Hello everyone, this is homework 23, dividing polynomials. So we're going to break down the cases. First we'll look at a monomial divided by a monomial. We actually saw this in the laws of exponents homeworks that we've experienced, and that's how we can do it. Just basically use your laws of exponents, or think of it as cancellation. Now the law of the exponents, if you're dividing polynomials, when we're talking about is the division. That is, in general, x to the m divided by x to the n is x to the m minus n. That is, we keep the base and we subtract the exponents. So something like x to the 8th over x, you could think of that as x to the 1st in the denominator. And with respect to the basic property, that would be x to the 8 minus 1, or 7. Now, thinking about that as cancellation, x to the 8th over x, there's really 8 factors of x. I'm not going to write them all out. Divided by x. And if you cancel one of them from numerator and denominator, we're left with 7 in the numerator over 1, so x to the 7th. Now that's helpful, the cancellation concept, when you're dealing with a situation like this, where there is a ratio of two powers that have a common base, and the exponent on the variable in the denominator is greater than the exponent on the variable in the numerator. So thinking about it as the division rule, we'd formally have x to the 3 minus 5, which is x to the negative 2. But then you should recall that x to the negative m, or negative exponent rule, is 1 over x to the m. So that would be 1 over x squared. So it's actually easier to think about this in terms of cancellation. Now, excuse me. You don't have to show the expansion of x cubed over x to the 5th. All you have to do is think about the fact that x cubed really means x times x times x, 3 factors of x. X to the 5th means 5 factors of x, x times x times x times x times x. And if you cancel out 3 common factors, you're left with a 1 in the numerator, and you're basically subtracting 3 factors of x. You're taking away 3 factors of x from x to the 5th, and you're left with x squared. So you're still subtracting the exponents, but you're doing it in a more advantageous way to avoid the negative exponents. So when you have a situation where there's more than one variable, it's your choice. You can recopy it by maybe grouping the common bases together. So I group the p's, p to the 5th over p squared, and q to the 3rd over q to the 7th. And then think about cancellation. This would be p cubed over 1, or subtract the exponents, however, but cancellation's better, because here the denominator has a power that's greater than the numerator, so you can cancel 3 factors. You'll be left with a 1 in the numerator, and taking 3 factors away from 7 factors, we're left with 4 factors of q, or q to the 4th. And then we get p cubed over q to the 4th. And you didn't have to separate them. You could have actually just jumped right in here and started the cancellation process. When you're dealing with coefficients, just be careful. 20 over 5, maybe I'll separate them here. Alright, this is k to the 1st in the denominator. So I guess this one's simple enough. 5 goes into 20 evenly 4 times. And subtracting the exponents, or thinking about it as cancellation, left with k to the fourth. But then here's one that's a little bit more interesting. If you separate negative 16 over negative 4 and m squared over m to the fifth. Okay, well, the double negatives make positive, and 4 goes into 16 4 times. I'm going to write it as 4 over 1. See, and here's the situation again where the variable in the denominator has a greater exponent than the variable in the numerator. So thinking about this in terms of cancellation, take away 2 common factors, we're left with the 1 in the numerator, and taking away 2 factors from 5 factors of m, we're left with m cubed in the denominator. And then we can multiply across and get 4 over m cubed. And again, if you just jump right in here and you cancel, this goes into negative 4 goes into negative 4 once, into 16 4 times, and then you can cancel these m squareds out and cancel this m cubed, m to the fifth, and you're left with m cubed. If you just want to show it that way, that's fine, okay? But I'm going to take the time to show it a little bit more literally. And I'm going to separate things. So negative 10 over 5 times a to the seventh over a times b over b to the fifth. And canceling 5 with 10, we get 2, so negative 2. I'm going to say it's over 1. This is a to the first in the denominator, so think about cancellation or division of common bases, your choice. Left with a to the sixth, I'm going to say over 1. And the reason why is because here I see a situation, the reason why I left them over 1s, that is because here I see a situation where we have a greater exponent in the denominator again. So b to the fifth, b to the first in the numerator, take away 1 factor of b, we're left with 1 in the numerator, and 1 factor away from b to the fifth, we're left with b to the fourth. So negative 2 a to the sixth over b to the fourth. And then a final example. Again, I'll separate things, but you could just jump in right in there and note the cancellations. There's actually nothing to cancel with regard to the coefficients. 7 over negative 3 or negative 3 over 7 is basically preferred. Here, it's easiest to think about x to the 8th over x to the 8th as a cancellation to get 1 over 1. Now, you could think about it as subtracting exponents. You'd get x to the 0. But remember, by definition, we had to find x as 0 to be 1. So if you wanted to think about it that way, that would be fine as well. But then concerning the y's, notice again the bigger exponents in the denominator. So think about cancellation, take away 4 factors, we're left with 1 in the numerator and 5 factors of y, or y to the fifth, in the denominator. Now also remember that when we have a fraction with the negative in the denominator, we prefer to have the negative associated with the numerator. So it looks like negative 7 over 3y to the fifth. So that's dividing a monomial by a monomial. Basically use the laws of exponents. But if we have a polynomial divided by a monomial, we use the property of combining fractions in reverse. That is, to combine fractions, we need a least common denominator. Often we say LCD. And so in general, if we have it, an example, a over c plus b over c, we have that least common denominator. You keep it and you combine the numerators, a plus b. We're basically going to reverse this process. And if we have a monomial denominator, essentially what we're saying, I'm going to rewrite it over here just to illustrate what I mean. What we mean is this denominator can get divided into each term of the numerator. So everything in the numerator gets divided by that denominator. So a gets divided by c, and then we have plus b gets divided by c. So we're essentially reversing our property for combining fractions. And just to note, we could extend that property to more than two terms. So when you see division of more than one term in the numerator over a single term, just take the step to exercise that property in reverse, okay? And divide everything by that denominator. So 12x to the 8th gets divided by x, and then plus 6x to the 5th gets divided by x. So you do need to take the time to show that step, and then you can think of division of common bases, cancellation, whatever you prefer. We understand, of course, the exponent's 1 on this x, so that'll give us 12x to the 7th, and then plus canceling one factor or using division of common bases rule to subtract the exponents, 6x to the 4th. Okay, and then here's an example where we're extending it now to more than two terms in the numerator. But the idea again is that everything's going to be divided by this denominator. So take the time to show it explicitly. 9x cubed gets divided by 9. Minus 81x squared gets divided by 9. Plus 18x gets divided by 9. And minus 54 gets divided by 9. And then you can cancel. And here we're just canceling coefficients. 9 goes into 9 once, so 1x cubed, just simply x cubed. 9 goes into 81 9 times, so minus 9x squared. Plus 9 goes into 18 2 times, so plus 2x. And then minus 9 goes into 54 6 times. So that's all there is to that. But now we see a few more examples where there's some variables, again, involved in the denominators. So just take the step to rewrite with that property of dividing that denominator into each term of the numerator. So just recopy the terms in the numerator, in this case 9p to the 5th, and show that you're dividing by 3p to the 4th. And similarly, plus 15p squared divided by p to the 4th, 3p to the 4th, that is. And here's where it's easier to think about cancellations now. Rather than showing explicitly like I've done in the past, you could think that 3 goes into 9 3 times, or 3 goes into 3 once, 3 goes into 9 3 times. But then these common factors of p to the 4th and p to the 5th are canceled to leave us with p to the 1st in the numerator. So that's just 3p to the 1st over 1, or 3p. But then in the second term, thinking about cancellations, okay, again, you can do a 3 goes into 3 once, into 15 5 times. But now when we cancel, we're taking away 2 factors of p from the numerator, replace that by 1, take 2 factors of p from the denominator, and we'd be left with p squared. So then this term is 5 over p squared. So a little bit different. Here's an example, extending to more than 2 terms, variables involved. Again, just take the step to recopy each term of the numerator divided by that term in the denominator. So negative 10x to the 6th gets divided by 5x squared, plus 25x squared gets divided by 5x squared, and the minus 25 gets divided by the 5x squared. And then we think of cancellation, however you like it. 5 goes into negative 10 and negative 2 times. X to the 6th over x squared is x to the 4th. Subtracting exponents or thinking of cancellation. Here, 5 goes into 25 5 times, and these x squareds cancel. So we just simply get plus 5 there. And then here we have minus 5 goes into 25 5 times, but this x squared that's in the denominator has to stay. And then here are a couple more that are just a little bit more complicated, but let's see, using our rules. Again, take the step to recopy. Numerator m cubed n squared over m squared n to the fourth minus m squared n cubed over m squared n to the fourth. So again, each term in the numerator gets divided by that term in the denominator. Then let's think about cancellations. Okay, larger exponent in the numerator, so there's an m in the numerator. But notice larger exponent regarding n is in the denominator. Take away 2 factors and we're left with an n squared in the denominator. And then here, the m squareds just literally cancel, replaced by 1s if you like. And the factor of n, again, the power is greater in the denominator. So taking 3 factors away, we're left with 1 in the numerator and n to the first in the denominator, or just simply n. And now finally, the last example, everything again gets divided by that denominator. So 6x squared y gets divided by 6xy plus 18x squared y squared gets divided by 6xy, and then minus xy squared gets divided by 6xy. And then we want to think of cancellations. Here the 6's cancel. X and x squared, we can cancel 1 factor of x, we're left with an x. And the y's cancel literally. So the only thing that really happened in this example was the x squared over x to the first. Everything else canceled neatly. Here, 6 will go into 18 3 times. This is x to the first and y to the first. Thinking about cancellation or division of common bases, there's an x and a y left in the numerator, so plus 3xy. And then in this term, well, that 6 is just going to have to stay in the denominator. We could think about canceling the x's completely, but then y squared over y will leave us with 1y in the numerator. Okay, and then we get to a final concept with regards to division, which we're going to go through this example and show something kind of interesting, but I'm not going to actually test you on this. But first off, when you divide a polynomial by a binomial, you have to go through the long division process. So recall the long division algorithm. If we had to divide 156 divided by 13, we'd put the 13 out in front of the 156. So this is our division algorithm, recall. And we start the division process. 13 doesn't go into 1, but it goes into 15 one time. 1 times 13 is 13. And then recall we subtract. And we get 2. And then we bring down the 6. And 13 goes into 26 2 times. And 2 times 13 is 26. And then we subtract. And in this case, we get a remainder of 0. I just wanted to remind you of the division algorithm. And that's done with polynomials. What we do is we set up the denominator, just like when we dealt with numbers, the denominator goes out in front of our division box. There's a lot of subtle points that we'll learn about in our next math course, but for now, we're just looking at the fundamentals, and all you have to remember is that when you see a polynomial divided by a binomial, you have to go through this arduous process. So the numerator we'll put under our division box. And formally, you have to make sure everything, all places are accounted for. And they are. I set it up that way. And then you focus on the leading terms. Just like we said, 13 goes into 15 one time. Just focus on the leading term and say x goes into x squared how many times? Or maybe more efficiently, what can I put here that when multiplied by the x gives me x squared? And that would be x. And then if I multiply x times x, we get x squared. And then multiply x times plus 6, we get plus 6x. Notice how the x's and the x squareds lined up neatly. And then we're going to subtract. And when we subtract, the x squareds go away. X squared minus x squared is 0. 7x minus 6x is 1x, or just simply x. And then just like our division algorithm, we bring down the 6. And then we focus on the leading terms again. X divides into x how many times? Or maybe more efficiently, what can I put here that when multiplied by x gives me x? And that would be a plus 1. And then when we multiply 1 times x, we get x. 1 times 6, we get plus 6. And when we subtract, we get a remainder of 0. So therefore, we're saying that x squared plus 7x plus 6 divided by x plus 6 actually reduces to just x plus 1. And a quick check, and this is the interesting part. So even though I'm not going to be testing you on this long division algorithm, this lends itself to something we're going to be doing in the next unit, which is extremely important. The fact that if we take our quotient, x plus 1, and we multiply it by the divisor, x plus 6, we should get the dividend, this numerator. And, of course, if we take these two, how are we going to multiply? And that is by FOIL. So x times x gives x squared, x times 6 plus 6x, 1 times x plus 1x, and 1 times 6 plus 6. Then we recopy the x squared, and we can combine the 6x and the 1x to get plus 7x, and recopy the plus 6. And so you can see that it checks. Okay? So, kind of interesting. Alright, so that's the end of actually unit test 4. It's going to be the test is going to be in class. We'll do a little review. I'll have a review video for you as well. And then we'll have our test. So we'll see you when you're ready for the review.